Have you ever just stopped and wondered how something like a car engine, or even just a simple pair of scissors, works with such perfect precision over and over again? Well, today we're going to pull back the curtain on the hidden science that makes all of that possible. It's called the theory of machines. No, I mean, really think about it. How do thousands of parts inside an engine, all those gears, pistons, and rods, move in perfect harmony? Instead of just crashing into each other and becoming a pile of useless metal. Well, the answer to that question is something that's really at the heart of all mechanical engineering, the theory of machines. You can think of it as the official rule book, right? It's the blueprint engineers use to build that incredible symphony of motion. So here's our game plan. First up, we'll get into the science of motion itself. Then, we'll break down a machine into its most basic building blocks. After that, we'll uncover the real secret sauce, making motion predictable. And finally, we'll put it all together and see how we get from a simple blueprint to a real working machine. All right, let's dive into our first section, the science of motion. So what exactly is this theory that basically governs the entire mechanical world? Okay, so the textbook definition is basically this. It's the science that studies the relative motion between the parts of a machine and the forces that act on them. But what does that really mean? Well, it's not just about stuff moving. It's about how parts move in relation to each other and why they move the way they do because of the forces involved. And that, right there, is the core knowledge you need to design anything that's going to work reliably. Okay, so how does this theory actually work in the real world? Well, it all starts by breaking down any machine, I don't care how complicated it is, into its two most basic, fundamental building blocks, and those are called links and pairs. So, the first building block is something called a kinematic link. Now, don't let the fancy name fool you. It's really just the engineering term for any single part of a machine that moves relative to some other part. But here's the key. It has to be what's called a resistant body. That just means it has to be strong enough to transmit forces without bending or breaking. A perfect way to think about it? It's like a single solid Lego brick. Let's look at this classic steam engine, for example. See the piston and its rod? That's one link. Then you've got the connecting rod. That's a second link. And the crank that turns the whole thing? That's a third. Each one of these simple, solid parts is a foundational building block for the entire engine. Okay, so what happens when you connect two of these links together? Well, you get what's called a kinematic pair. And this is where the magic really starts to happen in the design. See, a pair isn't just any old connection. The motion between the two links has to be constrained. All that means is it's forced to move in one specific, predictable direction. So if the link is the Lego brick, the pair is like the little studs and holes that dictate exactly how the next brick can snap on. And that word, constrained, brings us right to our third section. And honestly, this is the big aha moment in all of machine design, making motion predictable. This is the absolutely crucial step where engineers take what could be random movement and turn it into useful, repeatable work. Because at the end of the day, that's the whole game. It's not enough for parts to just move. They have to move predictably, every single time. This is the secret to designing a machine that doesn't just work once, but works reliably for years and years. So the gold standard, what every engineer is aiming for, is called completely constrained motion. Just look at this example, a square bar inside a square hole. It's super simple, right? No matter how you push or pull on that bar, it can only do one thing. Slide back and forth. It can't twist, it can't wobble. Its motion is 100% predictable, just because of its shape. But what about this? A round shaft in a round hole. This is what we call incompletely constrained motion. And why is that? Well, because it can do two different things. It can slide back and forth, and it can rotate. So the motion isn't definite anymore. It all depends on how you apply the force. And for most machines, that kind of unpredictability is a huge problem. So how do engineers get around that? Well, they use this really clever trick called successfully constrained motion. With this, the motion isn't controlled by the shape of the parts alone. Instead, you add an external force. Take this bearing, for example. The shaft could technically move up and down, but the heavy load pressing down on it prevents that from happening. So what's the only motion left? Rotation. We've successfully forced the motion to be predictable by using an outside force, like gravity or maybe a spring. And here's the big takeaway from all this. That whole concept of constrained motion, that is exactly why your car's wheels spin perfectly on their axle instead of just wobbling off. It's why a piston slides smoothly up and down in its cylinder. This predictability is the foundation of literally every safe and efficient machine that we rely on every single day. Okay, so let's recap. We have our building blocks, the links and pairs, and we have our main rule of the game, constrained motion. So now, in our final section, let's put it all together and see how engineers actually go from a simple blueprint to a finished machine. So when you start connecting a bunch of these links and pairs together and form a closed loop, you get something called a kinematic chain. The really important part here is that the last link has to connect all the way back to the first one. That creates a complete circuit where every movement inside it is predictable. You can think of this as the basic skeleton of any machine. Now, this brings up a really important difference we need to talk about, the difference between a machine and a structure. A machine, right, has parts that are meant to move relative to each other to get work done. But a structure, like a bridge or a building frame, is designed for the exact opposite. Its parts are not supposed to move. A machine is all about transmitting motion and power, while a structure is just there to transmit forces and stay put. Okay, here's the next super simple but absolutely critical step. You take that kinematic chain we just talked about and you fix one of its links. You anchor it. You bolt it down to the ground or to the frame of an engine. The second you do that, it's not a chain anymore. It becomes a mechanism. It's no longer just a floating loop of parts. It's now a system that's designed to create a very specific, repeatable motion. And what's the final step in this evolution? Well, you take that mechanism, you give it a source of power, like an engine or a motor, and you give it a job to do. At that point, it finally becomes a machine. So you can think of it this way. A mechanism is the idea, the concept of a motion. A machine is that idea put into the real world to actually get something done. So when you look at it that way, there's this really clear, kind of brilliant progression, right? A mechanism, that's the blueprint for motion. And a machine is that blueprint brought to life, built to do real work. It's the whole journey, from a simple part all the way to a functioning machine. So the next time you look at any machine, doesn't matter if it's a bicycle or a massive construction crane, try to see that hidden blueprint inside. See the links, the pairs, the constrained motion that makes it all possible. Now that you know the engineer's blueprint, what machines are you going to see differently?